Hi there. In the previous video, I mentioned that the purpose of NumPy is to make it easier for you to work with numbers within Python. And so in this and subsequent videos, we will begin to learn the different functionality of NumPy that make this so. Now, if you've worked with MATLAB already, you might find a lot of this pretty familiar. And in that case, I'd recommend that you check out this article from the NumPy documentation. It explains the differences in the syntax and in the approach between MATLAB and NumPy. And so it should make it easier for you to do this transition. In this video, we will be learning about the aggregations or the reductions. These are functions that take a NumPy array and summarize it down to a single number. Let's start with an example. As always, we'll begin by importing NumPy as NP, and now we're going to define an array with 3 elements called A, and it has a 1, a 4, and a 5. So we can get a sense of the methods that are attached to the array object with the period tab, the autocomplete functionality of Jupyter Lab. And we can see that there are many methods here. For now, we're going to try this one called sum. We call sum, and it gives us a 10. That's because the elements of the array, 1 plus 4 plus 5, equals 10. Let's look at the documentation for sum. We can see that it takes in several optional arguments. We'll have a look later at this first one, axis. Now there are other options, other good functions that we can use. The mean. That is the average of the elements. 1 plus 4 plus 5 divided by 3 is 3.33. Another thing worth mentioning here is that all of these summary functions that are available as methods on the array object are also available from the NumPy package itself as standalone functions. So what do I mean by that? If I ask for the directory of A, it's going to give me all of the functions that are attached to the NumPy array. And if I ask for the directory of NumPy itself, it gives me functions that are available just by virtue of importing NumPy. They're not attached to any array. And there are many of them. So how many are there? There are about 600. Okay. And I can get, for example, the mean by calling the mean function from NumPy and passing in the array. That's exactly the same thing as calling the mean function that is attached to the NumPy array. So there will always be 2 different ways of calling these functions, either by the method attached to the array or by a standalone method from the NumPy package. Here's a table of the different aggregations for numerical arrays. That's opposed to Boolean arrays, which we'll see in a bit. We've already seen the sum. This is the NP version, and as I just said, there's also the array version. This takes the array and optionally an axis. And it gives back the sum of the elements of A over the given axis, which I am abbreviating OTGA. And you can see that OTGA applies in every single case, so we can always pass in an axis to all of these methods. Okay, so then comes the mean. That is the mean of the elements of A. STD is the standard deviation of the elements of A. Prod is the product of the elements of A. Then max and min are the maximum or the largest of the elements of A and the smallest of the elements of A. And then argmax and argmin are the index to the largest or smallest of the elements of A. All right, have a look at this matrix. It has some numbers on the top and it has some mathematical constants on the bottom. And I have defined it here using the NumPy array constructor. And you can see that the constants, pi and e, I got them from NumPy. So let's run that. Now np.pi has been replaced with its value, and np.e has been replaced with its value. And there are other constants. There are np.nan, that means not a number, and np.inf, which means infinity. So those can come in handy sometimes. Okay, let's give this a variable name. And we know that if we want the sum of all of the elements in A, we can use a.sum. And if I add up all of these numbers, it gives me negative 1.84. But what if what we want is the row sum? By that I mean I want 1.7 plus pi, and then negative 4.3 plus e, and then negative 5.1 plus 0. So I want 3 numbers. Then that's where the axis argument comes in. I set axis equal to 0, and it returns 3 numbers. 1.7 plus pi turns out to be 4.84. And negative 4.3 plus e is negative 1.58. Okay. Now, this is how I think of axis. With axis set to 0, we're doing the operation in the vertical direction, so something like that. Whereas axis equal to 1, we do the operation in the horizontal direction, so like that. So setting axis equal to 1, in this case, we should get 2 numbers. Let's see that. Axis is equal to 1. I get 2 numbers. Negative 7.7 is the row, the sum of the items in the 0th row, and 5.85 is pi plus e plus 0. Okay, this also works with all of our aggregations. So I can take the product of the elements over in the horizontal direction. I can also take the max. So the largest of 1.7, negative 4.3, and negative 5.1 is 1.7. And the largest of pi, e, and 0 is pi. And if I ask for argmax, that's going to give me the column indices of these things. So 1.7 is in the 0th column, and pi is also in the 0th column. Those are the maximums of their respective rows. And if I did it with axis is equal to 0, just the max, then I would get that pi is bigger than 1.7, e is bigger than negative 4.3, and 0 is is greater than negative 5.1. And the argmax then tells me that those 3 elements are all in row 1. Okay, so that's axis. There are also aggregations for Boolean arrays. So these are arrays whose data type is Boolean. So all of their entries are either true or false. Everything that I've said about numerical arrays or numerical aggregations also applies here. In particular, there's going to be 2 versions for the aggregations, one with np dot and the other with, say, a dot. Also, the axis argument works the same as with numerical arrays or numerical aggregations. All right, we have 2 of them. There's all and any. All is going to return true if all of the entries in A are true. All of the entries in A or all of the entries along the axis specified by the axis argument. So it's going to return true only when all of the elements are true, something like that. On the other hand, np.any is going to return true if any of the entries in A are true. So it will return true unless everything is false. Let's have a look at this in the code. Here's an array. It has 2 rows. The first is true, true, false, and the second is false, true, false. So what do you think will happen if I run a.all? We get false, because not everything in A is true. There's at least one false, so a.all is false. How about a.any? It is true because there is at least one true. not everything in A is false. Okay, we can now use the axis argument. Let's pass in axis is equal to 0. We get 3 elements. The first true is because there is at least one true in the first column of A. The second is true because, again, there's at least one true in the second column of A. And the third is false because there are no trues in the third column of A. And with all, we have the first is false because there is at least one false in the first column of A. The second is true because everything is true in the second column, and then false because there's at least one false in the third column of A. Okay, that does it for the aggregations. Next, we're going to view in the next video the operations that we can do on NumPy arrays, and these together are going to give us a really powerful tool for doing numerical computations.